The Viete Relations, an introduction for polynomials. Here's some background on Francois Viete. He was born in 1540. He died on February 23rd, 1603. History remembers him as a French mathematician, but he was also a lawyer by trade in France. He was accused of sympathy for the Protestant cause in France during his life and was exiled to Fontenay for this accusation. Henry IV used him as a code breaker during conflicts that Henry IV was involved in. And his final essay was on cryptography, and this essay actually made all the encryption methods obsolete at the time. So I encourage you to check out his essays on cryptography if that's something that you're interested in. While many mathematicians were focused on solving polynomials, there were competitions in Italy and in France and in England where mathematicians would get together and try to solve these polynomials, trying to develop patterns and things. Viete Relations actually goes backwards. He knew that polynomials could be factored, although René Descartes in 1637, about 34 years after his death, after Viete's death, he actually used the factor theorem and stated it formally. So René Descartes is often credited with the formal statement of the factor theorem, but Francois Viete knew that polynomials had a factored form as we understand it today. So what he did, Viete, was that he just considered monic polynomials, though. And monic polynomials are polynomials whose leading coefficient is 1. So let's take a look at an example. The Viete Relations is a description between the coefficients of monic polynomials and their roots. Now, the quadratic formula is an example of how the roots are related to the coefficients of polynomials. So what we're going to do here is we're going to work backwards. We already know that polynomials can be factored. So we're going to write it out in a factored form. In this case, we have x minus a and x minus b, where a and b are the roots to a monic quadratic polynomial. And the factor theorem allows us to write it out in a factored form. Now, if we expand this by this foiling method, we end up with x squared minus the quantity a plus b times x plus a times b. And what we notice here is that the coefficient of x is the opposite of the sum of the roots, and the constant term is the product of the roots. So these conditions are often quoted on or expanded on when we're discussing factoring procedures for these quadratics. So this is one place where the conditions come from. Now, if we remember, when we factor quadratics, we often tell students that we're looking for two numbers whose sum is the middle term and whose product is the constant term. The AC method expands on this a little bit further by saying we need two numbers whose product happens to be the product of the coefficient of x squared and the constant term. So those conditions kind of expand on what Francois Viete established back in the mid-1500s, saying that we need that sum and that product kind of combination for quadratics. Now, when we take a look at a cubic polynomial, we're going to start establishing a pattern here. So if I take a, b, and c to be the roots of a cubic polynomial, and we expand this out, then we have x cubed minus the quantity a plus b plus c times x squared, plus the quantity ab plus ac plus bc, all of that times x, minus the quantity abc. So we have these conditions that we can see from the expansion that Francois Viete was alluding to. The coefficient of x squared is the opposite of the sum of the roots. The constant is the opposite of the product of the roots, and the coefficient of x is the sum of all possible pairs of products of the roots. So we kind of see a pattern growing here, okay, with the Viete relations. So the first and second conditions listed previously resemble the conditions we saw with the quadratic. The coefficient of x in the quadratic and the coefficient of x squared in the cubic was always minus the sum of the roots, or the negative of the sum of the roots. the constant terms in these polynomials end up being a combination of the product of the roots. Whether it's a positive or a negative, one multiplying it is based on the degree. Even degrees have a positive product of the roots, and then an odd degree would be -1 times the product of the roots. So when it comes to solving monocubic equations, we could use these Viete relations and generate a nonlinear system like shown here, where you have a plus b plus c has to be the opposite of the coefficient of x squared. AB plus AC plus BC is going to be the coefficient of x, and ABC is going to be the opposite of the constant term. Okay, so we could do this nonlinear system. This is one approach that you could try. If we wanted to solve x cubed minus 7x plus 6 equals 0, we're in luck. This happens to be a depressed cubic. So Cardano's equations or Cardano's formulas could come up and help us solve this stuff. And Cardano's formulas are here for solving a cubic. Now, Cardano was one of the first people to publish results on solving cubic equations. You can read about the history on that online. So here we have this u value, this v value, and then this t value, which happens to be the sum of u and v. For our particular example here, the q value in these formulas will be 6. The p value in these formulas will be -7. But as you can see here, solving the nonlinear system is very, very ugly. Solving these cubic radicals could also be very, very ugly. So we run into an additional complication because the quantity 4p cubed minus 27q squared is negative. We actually get 9 roots, and this is from the cyclic behavior of the complex solutions that come with this. So, but we only can have 3 because this is a degree 3 polynomial. So we would have to find out all 9 roots, and then whichever one of these 9 roots, whichever 3 of them actually, would actually solve our cubic polynomial. So rather than go through these ugly formulas that Cardano generated, or trying to solve a nonlinear system of equations, a 3x3 one in fact, we're actually going to use the Viete relations to see if we can use what the nonlinear system of equations is telling us, but in a more kind of conceptual way rather than a rigorous arithmetic way. So we're going to go through and we're going to say we have an integer coefficient polynomial. Now we know from the rational zero theorem that if the polynomial is monic and all of the coefficients are integers, then any rational solution would also be an integer. So if the solutions happen to be integers, then we also know from the Viete relations that they have to be factors of 6 because 6 was the constant term. So the product of the roots would have to multiply to 6, and if they're integers, then they all got to be factors. We also know that the roots have to sum to 0, and that there must be 3, okay, because it's a degree 3 polynomial. Now, all of these conditions here would be true whether or not they were integers, but because we have integer coefficients here, we're gonna see if at least one of them is an integer. So I'm going to use the idea that the fact that it has to be a factor of 6. Now, the only factors of 6 are 1, 2, 3, and 6. So what we're going to work out here is we're going to say, look, we know from the remainder theorem that if I plug in a number and its remainder is 0, then I know that x minus that number would be a factor. So I'm going to plug in 1 because I know 1 is a factor of 6. I'm going to plug in 1, and I end up getting 0 when I plug it in. So that means that 1 is a solution. So we know that x minus 1 is a factor from the factor theorem, and I can divide x minus 1 out and not have a remainder. So when I do that, I get x squared plus x minus 6. And we know that x squared plus x minus 6 can be factored into x plus 3 times x minus 2. And now we have all 3 of our factors. x minus 1, x minus 2, and x plus 3. So here we used the Viete relations as written up in the nonlinear system, but we used it in a conceptual way. And we made an assumption that said, hey, if these are integers, then I can start substituting some values in and seeing if I can generate other solutions. And in this case, I ended up getting pretty lucky that the answers were all fairly nice integers. So a little ingenuity went a long way here, and it helped us to avoid some complicated formulas or some complicated systems to solve. Some tools involved with Viete relations happens to be Pascal's triangle. Now there's a picture of Pascal's triangle here on the right, and the reason why Pascal's triangle is useful in the Viete relations is kind of demonstrated on the left here. Our quadratic example with x minus a times x minus b. We knew that if we folded out, we had x squared minus the sum of a plus b times x, and then plus ab. Well, we have one x squared term. We have a sum of two values that are multiplying x, and then we have a product of two values, which gives me one term. So here I have 1, 2, 1, and 1, 2, 1 happens to be a row in Pascal's triangle. When I do the cubic, I have a similar thing. I have 1x cubed, and then I have minus the sum of a, b, and c as x squared. So there's three terms there that are being added for the coefficient of x squared. And then I have three terms being added for the coefficient of x, which happen to be ab, ac, and bc. And then I have minus one term that happens to be the product of all the roots, which is abc. So here we have 1, 3, 3, 1, which happens to be the next row in Pascal's triangle. So this pattern that Francois Viete kind of developed with this idea was to say, look, if you have a monic polynomial and you start multiplying it out, then you know that the roots will satisfy these patterns. The sum of the roots has to be the opposite of the coefficient of the term that is 1 power less than the degree. Then as you move down in those powers, you start increasing the number of combinations of products of the roots until finally you get to the product of all of the roots for the constant term. So a quartic polynomial, and next to the fourth polynomial, according to Pascal's triangle, we have a 1, 4, 6, 4, 1 row. So we have one thing for x to the fourth. We have a plus b plus c plus d. Those are our four terms for x cubed. Then we have all of the products of two of the roots, all those combinations, ab, ac, ad, bc, bd, and cd. All of those are being added together, and those are all x squared terms, and there's 6 of them. And then you have 4 terms for the triple products, ABC, ABD, ACD, BCD, and those are all multiplying x. And then you have one term that represents the constant, which is the product of all of the roots, in this case ABCD. And the signs alternate as you go down. So there's a lot of patterns in Viete's relations, not just how many numbers you're going to be combining or how many terms you're going to be combining, but also the structure of each one of those terms. So we can think of the monic term, the one that's multiplying x to the fourth, as like a n choose 0, if you will, or a 1. There's an understood 1 there. Where here we would have 4 choose 1 for the number of cubing terms, and that would be 4. 1, 2, 3, 4. And then for the squared term, we would have 4 choose 2, which there are 6 ways to get that. So we know that there are going to be 6 terms, and we know that they have to be products of 2 of the roots. So all the possible products of 2 of the roots form up the 6 terms. And then all of the possible products for 3 of the roots form up 4 terms multiplying x. And then you have 4 choose 4, and that would be 1, and that would be the constant term that you're multiplying all the roots together. So let's look at another example. If a polynomial root has 1, 2, 3, 4, how would the standard form appear? Well, we know that if we use the factor theorem, we have x minus 1 times x minus 2 times x minus 3 times x minus 4. And if we start multiplying all of that out, the details are here, and we get x to the fourth minus 10x cubed plus 35x squared minus 50x plus 24. Now, this is a lot of multiplication, and we could possibly have some errors in our multiplication. But using Viete's relations, we know that the sum of the roots has to be the coefficient of x cubed. There were 4 factors, so this is an x to the fourth polynomial. So we know that the sum of the roots has to be the coefficient of x cubed. We know that the product of all of the of 2 of the roots, the sum of the product of 2 of the roots, all of that has to be the coefficient of x squared, which in this case happens to be 35. So 1 times 2 plus 1 times 3 plus 1 times 4 plus 2 times 3 plus 2 times 4 plus 3 times 4. Just add up all those numbers. The sum of the product of 3 of the roots, all the combinations of 3 of the roots, that actually adds up to negative 50 when I take the opposite sign. And then, of course, the product of all the roots has to be 24. So finding the coefficients, knowing the roots, using the Viete relations, boils down to just an arithmetic problem. Whereas before, if you try to do it directly by using the factors, now you have a lot of x's with powers floating around, which could lead to a lot of mistakes. So the Viete relations allow you to circumvent some of that algebra in favor of arithmetic. But again, you got to know the patterns. So other results attributed to Viete would be that he independently derived trigonometric solutions for cubic polynomials with 3 real roots. Okay, while Cardano and Tartaglia were doing their root finding, he was also able to identify cubic solutions. He did give algebra a foundation as strong as geometry, creating first symbolic algebra. So geometry had been in existence since the ancient Greeks. And so geometry was already a pretty well-established field of mathematics. Viete contributed to having algebra have just as strong a foundation so that it could be understood. It was said that he was the first mathematician who introduced notations for problems and not just unknowns. So what happened in this case was that he basically kind of modernized the approach to mathematics. So the medieval algebra that existed was very, very much on just, labeling unknowns, and the rules weren't very well defined. So what happened when Viete confronted this issue, his work started to rely more on computational efforts and not just statements of rules. So Viete had his hand in generating mathematics as we study it today, over almost 500 years ago now. So here are some questions for you to ponder, and if you wish, you can pause this little presentation to see if you can figure out these questions. And here are some more questions. Again, you can pause this to see if you can figure out the answers to these questions. Thank you for your time and attention.